the universe is expanding, galaxies are just hurtling through space, right? But what if you could actually, like, put a number on that cosmic motion yourself? We're diving deep into a concept that's not just for professional observatories anymore. It's a really powerful principle that helps us map the cosmos, and you can actually explore it right from your computer.
Yeah, what's truly fascinating here is how fundamental physics, specifically the properties of light, allows us to quantify such grand universal movements. Pretty amazing stuff.
Yeah.
So our mission in this deep dive is basically to unravel the theory behind how light reveals these cosmic speeds, and then using our source material, walk you through a simplified, hands-on demonstration. It really brings this incredible science within reach.
Right.
We're going to show you not just what redshift and blueshift are, but how accessible it is to apply these principles yourself to measure galaxy velocity.
Okay, so let's unpack this a bit. How does light, I mean, something we see every single day, become this kind of extraordinary messenger?
Yeah.
How does it tell us the secrets of moving galaxies?
Well, that raises a really important question. What exactly are we looking for in that light? The core idea is that light, when you spread it out, like with a prism, it reveals a spectrum, different colors or wavelengths. And here's the key bit. Every element in stars and galaxies, things like hydrogen or nitrogen, has a unique spectral signature.
Ah, okay.
They emit or absorb light at very specific known wavelengths. This creates distinct bright lines, we call those emission lines, or dark absorption lines in their spectrum.
Like a cosmic fingerprint, uniquely identifying the elements, maybe the conditions in a distant galaxy.
Precisely. Exactly like a fingerprint or a barcode. When we capture this light and analyze it, say, through a spectroscope, these unique lines become visible. Now, here's where it gets really powerful. If a galaxy is moving away from us, the wavelengths of these specific spectral lines appear stretched. They shift towards the red end of the spectrum.
Right, that's redshift.
That's redshift, exactly. And conversely, if a galaxy is moving towards us, these lines get compressed, they shift towards the blue end.
Blueshift.
That's blueshift. Simple as that, conceptually.
And the incredible part then is by measuring how much these lines have shifted from their known sort of rest wavelengths, we can actually calculate the galaxy's speed relative to us.
Yes, absolutely. The degree of this shift, how far the line has moved, allows us to calculate a value known as z. It's the redshift parameter, though it can be negative for blueshift. This z's value is, well, it's directly related to the galaxy's velocity. It's kind of the numerical key to unlocking its motion.
Okay, this is cool. Now for the hands-on part, because that's what makes this a fun space project at home, right? Imagine being able to actually perform this kind of measurement yourself using real astronomical data. Our source material guides us through a pretty fascinating way to put this theory into practice using the SDSS Sky Server Explorer. That's an incredible online archive, isn't it? Millions of galaxy spectra.
It really is. It's a fantastic resource. So you start by navigating to the SDSS Sky Server Explorer tool online. And by default, it often selects a galaxy to look at. In this case, Z2-2150 is selected. Its coordinates are given, RA, and it's like its celestial address, right? Pinpointing its location.
Like latitude and longitude, but for the sky. Got it.
Exactly. RA 229.52578755753, December 42.74583760.
Okay. And then you scroll down to the optical spectra section, click Analyze Spectrum. Now, when you look at a spectrum like that, what are the telltale signs for a redshift? What should you be looking for?
So what you often see immediately are distinct, prominent peaks in the graph, the spectrum graph. In this example for Z2-2150, these are NII emission lines. They come from ionized nitrogen. They're particularly useful because, well, they're often quite bright. They're found consistently in many galaxies, and crucially, they have very well-known rest wavelengths.
The wavelength they should be at if the galaxy wasn't moving relative to us.
Precisely. The ones we care about here are the NII 6549.86 angstrom and NII 6585.27 angstrom lines. You'd select those in the tool underlines, then spectral.
Right, and this is where the theory becomes visual, where you actually see the shift you mentioned.
Exactly. The tool has a custom redshift slider. You use that slider to basically shift the theoretical rest wavelengths of those NII lines until they line up perfectly with the observed peaks in the galaxy's actual spectrum. You want to line them up with the first and third main peaks you see there. You might need to zoom in a bit on the graph to get it precise.
Okay.
This alignment visually shows you the shift, and more importantly, the tool will tell you the shifted wavelengths where those peaks actually appear in this galaxy's light. For example, let's say you find they're now at 6813.967 and 6850.149 angstroms.
Ah, so you've got the rest wavelength, and now you've measured the observed wavelength.
Got it. The difference between those two numbers for a given line is the key.
So, okay, we have those crucial numbers. What's next? How do we get to the speed? You mentioned z.
Right. The next step is to calculate z, the redshift value. The formula is pretty simple. Z equals uh, observed wavelengths minus the rest wavelengths, all divided by the rest wavelength.
Z observed rest. Got it. You'd probably do this for both NII lines and average them for better accuracy.
Ideally, yes.
Yeah.
Or just use one reliable line. Once you have z, getting the velocity is straightforward.
And that's just V equals Z times C.
Yep. Velocity equals z times c, where c is the speed of light. That's about 299,792 kilometers per second. A big number.
Okay, so for this galaxy Z22150, using those example shifted wavelengths, what kind of numbers do we get?
Well, if you plug in those observed wavelengths, say 6813.967, and compare it to the rest wavelength 6549.86, you do the math, observe rest, you'd find a z's value of approximately 0.04, give or take a little, depending on your precise measurement.
And it's positive, which means
Positive means redshift. It means the galaxy is moving away from us, as expected for most distant galaxies due to the universe's expansion. Now, when you plug that z of 0.04 into the velocity formula, v equals zle, you get a velocity of roughly 12,096 kilometers per second.
wow, 12,000 kilometers per second. That really hammers home the scale we're talking about, just immense cosmic motion.
Yeah.
And what's really empowering here, I think, is how you can actually check your work, right? Our source shows us how to double check this using Simbad.
That's right. Simbad is basically a huge professional astronomical database. You can search for almost any known object. So if you search for Z22150 on the Simbad website, you can look up its known properties. And you'll find its listed radial velocity is around 12,014 kilometers.
Hey, that's really close.
It is. And its listed Z's value is about 0.041. So our quick calculation using the online tool gets remarkably close to the professionally measured value.
Mhm.
It really highlights how, accessible and pretty accurate these methods can be, even for someone just exploring this at home.
That's fantastic. And for those listening who want to actually try this themselves, really solidify their understanding, the source material gives us a bit of homework, doesn't it?
It does, a little challenge. Apply these same steps, find the galaxy, analyze its spectrum, identify lines, measure the shift, calculate z's, and then velocity for another galaxy called LEDA 2196454. See what speed you get.
Cool. A great way to practice. Okay, so wrapping up here. Today, we've really journeyed from just, looking at light to understanding its subtle shifts and then actually quantifying the immense velocities of galaxies across the universe. Just imagine, by following these steps, you can measure a piece of the universe's expansion right from your own home. That's pretty wild.
It truly is profound, isn't it?
Yeah.
This ability to quantify the universe's dynamics. And it all stems from these basic principles of light and how elements interact with it. And if we connect this to the bigger picture, this seemingly simple measurement, redshift, was fundamental. It led Hubble to realize the universe wasn't static, that it was expanding.
Right, Hubble's law.
Exactly. And eventually, that path led to discovering dark energy and the accelerating expansion. It all started with carefully looking at these spectral shifts. It just underscores how powerful fundamental scientific inquiry can be.
So, thinking about the broader significance then, the next time you look up at the night sky, maybe consider those incredible forces at play and the fact that you personally have the tools now to measure them, at least in principle. What does it tell you, about our place in this vast expanding cosmos? That such profound measurements, the ones that underpin our whole understanding of the universe's history and maybe its future, that they can be made with methods that are, relatively speaking, pretty straightforward. Something to think about.